guys. I did decide to do on video just 4 little questions that I asked you to do today. I really think that finding the area with polar is probably the hardest part of this section. So I thought, you know what, let's just do one extra little practice. You'll be super excited to know that there shall be no homework assignment today. Yes, I know. You're welcome. You're welcome. You're welcome. We're just going to do these 4 questions, and hopefully you did them before you're watching this video, and now you're just going to check them out and see how you did. I'm also just going to sort of walk you through them, how I would do them. And so I'm just going to write on a whiteboard over here on the side. So I am going to switch cameras super quick. You'll still hear my voice the whole time, but we're going to switch cameras over to the Elmo. I totally brought it home. I mean, duh. Teacher's not a teacher without their Elmo. And so I'm just going to go ahead and do this stuff right here. So this is the 4 square questions for polar practice for section 11.3. I'm going to erase this up and we're going to get our first question. So the first question on the 4 square worksheet, I don't have it in front of me, but I definitely have the question. And it says, what is the area inside one loop, just one loop of this lemniscate? So it's the area inside of one loop. And so let's go ahead and do that. Okay, so the first thing we're going to do is we are going to graph this guy. Now, you could totally graph it on your graphing calculator. It will totally work. I'm going to go ahead and just graph it by hand. For the graphing calculator purposes, though, you do need to change this into just be r equals and then do the square root of 4 cosine of 2 theta. You can leave it just like that. One thought is that it is plus or minus when you take the square root, but it actually loops on itself, so it doesn't matter, okay? So let's go ahead and draw this guy's picture. So if we do this picture, it's a lemniscate. So remember, the funny thing we like to say is we lemniscate in a figure 8 on a double date. So I knew with the r squared and the 2 theta right there that it was going to be a lemniscate. The petals, each loop is just out to 2 because that is how the square root of 4. And then it just loops around like this. And it basically just wants the area inside one of the loops. So I'm just going to make it easy on myself, and I'm just going to do inside this loop right here, okay? What I'm actually going to do, though, it's a little bit clever, is I'm not going to do the whole loop. Instead, I'm just going to take and do half of it. Okay, so I'm really just going to do this half right here, and then I'll just double my answer, which I thought was a really clever thing to do. Okay, so we learned, I think it was in yesterday's lesson, that the formula is going to be 1/2 the integral. You pick your 2 theta values, theta 1 and theta 2, or alpha and beta. You do the r squared, and then you do d theta. And so that's exactly what we're going to do for this guy. So let's go ahead and do this. So I'm going to do the integral. And then I'm going to, again, I'm going to double my 1/2. Okay, just going to make that easy. And then I'm going to take my function, which is the square root of 4 cosine of 2 theta, and I'm going to square it. Okay, and then we do our d theta. I actually think that that's not horrible. What is a little bit tricky is finding the limits of integration, and that usually is the hardest part. So if we think about it kind of logically, okay, right here would be when theta equals 0, and then it's going to travel this way and trace. And so then we need to figure out where theta equals 0, and then right here where r equals 0. Okay, so this is definitely theta equals 0. So I am going to go a 0 down here for my lower limit of integration. Hopefully you can see that. And then I'm going to figure out the top limit of integration. So for my top limit of integration, I'm going to have to go over here and do a little sidebar information here. I need to know where this guy equals 0. So when is the radius equal to 0? Because remember, when we graph in polar, you're going out a certain number of steps. And when I get to this spot right here, I'm at no steps. I'm just kicking it. So where is this happening at? So I'm going to put the equation equal to 0 squared. I'm going to divide by 4, and I still get a 0. And then I have to think, where in the world does cosine equal 0, and then make that be where 2 theta is equal to it. So I'm thinking to myself that 2 theta would be, let's see, where does cosine equal 0? Cosine equals 0 at pi over 2, at 3 pi over 2, etc. Okay, so I'm just going to go ahead and take this first one right here. I don't need this next one. It is true, but I really just need that first spot. And so that gives me a theta equals pi over 4. I'm going to make that be my top limit of integration for pi over 4. I'm going to clean this up just the teensiest little bit. And so I get that the area is equal to, the 2 and the 1/2 cancel. I'm going to have the integral from 0 to pi over 4. And then the squared and the square root cancel. So it's just literally 4 times cosine of 2 theta d theta. I am not going to do any of these by hand. I'm literally just going to put them in my calculator. And so I'm actually thinking, instead of like switching screens, why don't I just use the graphing calculator right here? So maybe I'll zoom in on the calculator super quick so you can see what's happening. And whoop, let me get it on the screen. Okay, everything's backwards, like on the screen that I see, so it's a little bit tricky sound. So let's just make sure that we are in radian mode and then in polar, which is perfect. And so I'll roll with that. And I'm going to scooch this over so I can see what the heck I'm supposed to be putting in. So right now, I'm just going to put in this guy right here, right? So this is the guy that I'm now putting in my calculator right here. And let's see what that equals. So we're going to go to math. We're going to go down to number 9. We're going to go from 0 to a pi over 4. And then in here, we're just going to write 4. Oh, you can't even see that. I'm so gross. Sorry, guys. Let's get the tint on that a little bit better. Okay, so we're going to do 4. And then, oh, that is so much better. Sorry, guys. I had to get that adjusted. 4 times cosine of 2 theta. Close that parenthesis. We're golden. And put my d theta. And look at that, guys. The answer is 2. That's it. Literally, the answer is 2. Okay. So let me zoom back out. We're going to have an answer of 2. And that is Foursquare question number 1. So there you go. Let me zoom back out on that guy so you can kind of see it all at once. Okay. So there it is. There's the whole shebang. And there's number 1. Okay, let me get erased, and let's go ahead and do number 2. So erasing. And let's go to number 2. Okay, number 2 says that there is a looped limison. Okay, so this is number 2. The equation, I'm actually going to rewrite the equation to just be r equals -1 plus 2 sine of theta. Just a little rearrange for my own brain because I'm used to it looking like this. Okay, and then we're going to go ahead and graph this guy, and it says it wants the area inside of the smaller of the inside the loop. Okay, the loop that's so teensy meensy. So I am going to draw this guy's picture, and I am just freehanding these, right? You could graph them on your graphing calculator; it will work just as fine. But I'm just going to do this. Most of it is in the positive sign direction. It goes up to a 3. And it's going to loop back into a 1, and then the bump value is just a 1 on the sides. And so it looks a little bit like this. Remember, I'm freehanding this, so it isn't the bestest picture in the universe. But it would look something like that. And then all they want is the area of this inside right here, inside, okay? And for the inside, I just need to find, basically, again, it's a matter of finding those limits of integration. Those are always tricky right there. Okay, so let's get this set up to go. I'm going to do, the area is going to be 1/2. I'm going to come back to those limits in just a moment, right? And then I'm going to take the function, which is a -1 plus 2 sine of theta. I'm going to square that guy, and then I'm going to put my d theta. Okay, so really it's a matter of the limits of integration. So if we're thinking about this, you guys, the first thing it does is it, like, where it traces the path, right? It traces the path, and then where would like the first guy actually end up? And so you have to think about that when you think about the radii are big, but then they like get smaller, and then it's 0. Then it treks around like this, and then it goes back to 0 again. So I am looking for the limits of integration, I am looking for where, okay, so I'm looking where where r is equal to 0. That's what I'm looking for, where r is equal to 0. So let's find that, okay? Where does r equal 0? So I take my equation and I say, all right, 0 equals -1 plus 2 sine of theta. Bump some things around here. Move that 1 to the other side. So 1 equals 2 sine theta. Divide 1/2 equals sine of theta. And now we're literally just thinking, where in the world does the sine of theta equal a positive 1/2? It equals it right here for that little picture and right there. So this is a pi over 6, and this is a 5 pi over 6. And lo and behold, you guys, I have found my limits of integration. So I'm going to go up here. I'm going to make this be a pi over 6. I'm going to make this guy be a 5 pi over 6. And that right there is going to go in my calculator. So let's get this guy zoomed up again, zoomed in super close, super close, super close. Whoops, wrong way. Jeez, Mrs. Fox, really get this organized here. And let's go ahead and put this in. So I can still see the equation. I don't know if you can. You probably can't, but I can. So here I go. I'm going to go 0.5 times. I'm going to pull up, whoops, I'm going to do math. I'm going to do math, number 9. Sorry, guys. And then I'm going to put my lower limit of integration is a pi over 6. My upper limit of integration is a 5 pi over 6. And then the equation that I'm going to put, I'm going to have to do a parentheses. I'm going to go -1 plus 2 sine theta. I have to close the sign with the parentheses and then close the function and then put squared and then do a d theta. Okay, so that's that guy right there. I'll go ahead and put enter and it's going to spit out the answer. I mean, ooh, so exciting. The answer to this question is simply 0.544. Remember, guys, it is traditional. We are using our traditional 3 places like we do in calculus. We always like to do 3 places, and that's what it looks like. Okay, so all done with that one. Looks gorgeous. I'll zoom back out so you can see it all together if you're just kind of jamming through here, and that would be what the answer looks like. So there is number 2, just like that. Okay, so number 2, and we got it. Okay, let's go ahead and erase this and do number 3. Here we go for number 3, coming right up. So number 3 asks us to find, if I'm not mistaken, it asks us to find, okay, well, first of all, it gives us 2 equations. So let me get number 3 written here. And it says that there's 2 equations. There's a circle that has r equals 2, and then there's a cardioid that is 2 minus 2 cosine theta. So before I go anywhere, I really think that I should probably just draw this picture here. So let's get this picture drawn. I need 1, 2, 3, 4, pretty much 4 on each side just to make my picture look nice. The circle is just an r equals 2. And you know what, guys? I think I'm going to use 2 different colors on this just for fun. Let's make the circle just an r equals 2. So that's not horrible. Doesn't kind of look like a weird pancake, but you know, that's totally okay. Pancakes are fine when you're hand drawing. And then we're going to do the cardioid. So remember, the cardioid has the bumps, but it goes to the origin. This guy's mostly over here on the negative x-axis. And so it's 4 out because 2 plus 2 is 4. The bumps are right here and right here. And then it looks like a weird, you know how the cardioid looks. He looks like a weird, like tomato looking weird, funny guy, just like that. Okay, so we have those 2 guys. Now, what they actually wanted on this question, okay, it says they want it, what is being shared. Ooh, shared by the 2 figures. Okay, and so if we want what's being shared by them, it's actually, this is so interesting. It's actually this part right here, and then this part right here. So you know how on like other examples, we sometimes do like when there's 2 figures, you do the outside radius and the inside radius. Like if you're, I'm just going to draw a random picture down here, right? So if you've got like lemma, I don't know, something like this, and then like a circle. I don't know, guys, I'm making stuff up. It'll be like, I want this stuff in here. And so you draw your, nope, JK, hold up. Do an erase on that one. I was totally kidding. Let's do that one more time. Okay, so we've got like a figure, and then let's just do a figure over here. And so say like they want this stuff over here. What we do is we go and we say, okay, I want to take a radius of a spike out, and it has the outside curve and the inside curve, just like that. Okay, but when you look at this picture right here, this is just super fascinating. I am not kidding, guys. There's not an outside curve and an inside curve. Mrs. Fox, what are you saying? I'm not kidding you guys. These bumps right here are only going to the bumps. That's it, just to the bumps. Okay, this part over here is only going to the circle. That's it. There's no inside outside. It's actually just 2 parts. And you're just going to be adding those 2 parts together. I know. I can't even believe that happened. It's super crazy. So let me back out of here and think about these two parts that I am going to do, okay? So one of the parts that we're going to do is the bump part, and the other part is the circle part. Now, guys, there is lots of ways that you can organize this. You can double things, you can all sorts of things. So I'm just going to like write something down. And if we get the same answer, then we're totally fine. So I think what first I'm going to do is I'm going to try to do the bumps part. Okay, so the little bumps on the cardioid, I'm going to try to do that first. I'm going to zoom out just a smidge. And so I'm going to actually probably just do one of the bumps. I'm going to do this guy right here, just this part. Okay, so I'm just going to do this part of the bump. And so this is going to be, and then I'm going to double it to get this guy down here. So I'm going to go 2 times 1/2 in front of the integral. Now I know for the bumps, it's the cardioid. So I'm going to go 2 minus 2 cosine theta. Quantity squared d theta, because that's the r value. And now I need my limits of integration. Guys, it just follows like a normal trig stuff. So this guy right here would be in theta equals 0. This is up here when theta equals pi over 2. If you needed convincing on that, you could go ahead and set this guy equal to what that value is, which is a 2. And if you can say that 2 equals 2 minus 2 cosine theta, then you'll totally get a pi over 2 right there. So that's for the bumps part. And now we're going to add, right? We're going to add the half circle. It's really just a half circle. So in reality, guys, you don't even have to do calculus for the half circle. Like, I'm not even kidding. You could literally just take half a circle. You could just go, there's more than one way to do this. You could do 1/2 of pi, and then the radius is 2. So 1/2 of pi 2 squared. You could do it with calculus. You could say, I might go 2 times 1/2, and I might just get this part right here. Okay, find this part right here using some calculus, and that would be the integral from a pi over 2 over to a pi, as this would be like pi over 2, and then rotate over here to a pi. And then the function is really just 2 squared d theta. Literally any, like this way right here or this way right here, you're going to get the exact same answer. It doesn't matter. So let's go ahead and shove this into our calculator. Isn't that kind of cool that you can do the area sometimes in more than one way? Right, I agree. That is pretty fantastic. And so let's go ahead and zoom in on this guy. And I think I'm going to just scooch this over so that I can figure out what the heck I'm putting in my calculator super quick. Okay, so let's see if you can see that. I think you can. Maybe if I start typing. No, not really. You have to put it back on the board. Okay, so here we go. Let's do this, Mrs. Fox. So we are going to do the first guy. The 2 and the 1/2 cancel. And so I'm just going to go the integral from a 0 to a pi over 2 of the quantity. It's the cardioid. 2 minus 2 cosine theta. Quantity squared d theta. And then I am going to add another integral. So I'm just going to scooch this over for myself really quick. Okay, we're going to add the 2 and the 1/2 cancel again. And it's the integral from, okay, I can scooch it back. It's going to be the integral from, so math 9, from pi over 2 to pi. And then the function is just 2 squared. So I'm just going to put 4. And then I put d theta. And I enter that in my calculator. And ta-da, we have a beautiful answer of 7.708. That is the correct answer for this question number 3. So 7.708 is the correct answer. There we go. All right, we only have one last question, number 4. So let me get this baby erased. And we're going to go for our last question. So number 4 says we are going to be taking a circle, whoops, let me get this scooched over here, a circle and then a pedal graph, okay? So the two equations are a circle. The circle is r equals 2. The pedal graph or the rows is r equals 4 cosine of 2 theta. So this means it's 4 pedals because it's a 2 theta, and then you go out 4. So let's go ahead and get this guy drawn. Okay, so I'm definitely going to need out to 4 again because the lengths of the pedals are out to 4. 1, 2, 3, 4. So the circle is just at 2 for a radius. And, ooh, not horrible, you guys. One of my better circles, I'm just saying. And then we're going to do a pedal graph. So we're starting on the x-axis because it's a cosine. And so this is a spot for a pedal. This is a spot, this is a spot, and this is a spot. And then technically when you draw this petal graph, like if you were actually tracing it, you would trace it in this way. I don't know if you're watching my hand sort of graph this up. This is not horrible, you guys. I'm not even kidding. Okay, that totally deserves another. Yeah, because that's like some artwork right there. Okay, so what they wanted then, they said they wanted the area of all the things that are inside the petal graph, but then outside of the circle graph, okay? So I'm going to go over to my picture, and I'm not going to color all of them in. I'm actually just going to color one little piece. This is basically what they want. But how many of them are there? There's 1, 2, 3, 4, 5, 6, 7, 8 of them. So it's that little piece times 8. And I think that's what I'm going to do. So when I do my integral, I'm going to go 8 times 1/2. We're going to do the limits of integration in just a moment. This one totally does this time have an outside guy and an inside guy. So when I graph like one radius, like from the origin, there definitely is an outside curve and definitely an inside curve. So the outside curve is your petal graph. So I'm going to go in parentheses. Actually, I'm going to switch colors. That would be silly. Mrs. Wells, what are you doing with the wrong colors? Just ruining your whiteboard work. So we're going to take the 4 cosine of 2 theta quantity squared. So that's the outside guy. We're going to minus the inside guy, which is just a 2 squared. I am going to make that guy be d theta, and now the only thing we have to figure out is the limits of integration. But as I was saying earlier, that usually is the hardest part, is the limits of integration. So I'm thinking that we're going to go from here all the way to here. So we need to figure out what this angle is and what this one is. Well, I'm pretty sure that this one right here is going to be 0, okay? So that's our first limit of integration. It's going to be 0. But where is the other one? A nice way to get this limit of integration, I'm just going to kind of go down here, is to think about where they intersect, okay? So they are actually at the exact same spot right there, right? And if we can figure out where they intersect, then I'm going to be totally golden. So where would these two guys, these two equations be the same thing? So let's just maybe plug in this 2 for R. So I'm going to go 2 equals 4 cosine of 2 theta and figure out what will make this happen, okay? So to make this happen, let's divide by 4. So we get 1/2 when I simplify is cosine of 2 theta. Where does cosine equal 1/2, a positive 1/2? It would be like right here and down here. But really, I just need, that's a bad triangle. I really just need this first one right here, because it's just the first spot that it happens. So I'm thinking we're going to say that 2 theta is equal to the angle of pi over 3, which means now your theta is a pi over 6. So now I'm going to go up here, and this guy is going to be a pi over 6 up there. Okay, that is exactly what I am going to put into my calculator. Okay, so let me just get that guy zoomed in super, super close again, and we're going to put this in our before I do that, out in the front, guys, the 8 and the 1/2 totally simplified just to be a 4 in the front. So that is what I'm going to do in my calculator. So let's get this baby zoomed in, zoomed in, zoomed in. Here we go. And let's put this in. So I'm going to go 4 in front. Oh, Mrs. Fox, you're all tilty crazy. What is happening? What is happening? Hold on. Get organized. Here we go. Okay. So we're going to go 4 times the integral. And we said it was going to go from a 0 to a pi over 6. And then this is going to be a pain to put in, okay? But I need a parentheses. I need a 4 cosine of 2 theta, close the theta, close the first function squared, minus 2 squared is actually just 4, and then put my d theta on the outside. And here we go. That is the answer, 15.306. Let me write that down. Okay, 15.306. And ladies and gentlemen, that is how lovely it can be when we do our polar areas, okay? It is all about the limits of integration. Once you get those limits of integration down, then it's actually like kind of amazing. So let me go ahead and flip back to the screen just so you can see my face again because, right? So cute. I know. Okay. So ladies and gents, that's all you have to do. So that was your whole entire activity for today. I wanted you to try those questions on your own. Check them to see if they make sense. Hopefully they do. And that's it. Okay. Coming up to end out the week, we're going to do sort of like the group quiz, which just means I'm going to issue it to you guys. You're going to do it as an assignment. And then the next day I'll have a video kind of like showing you the answers and you can check it out. And I think that's it. Okay. Ladies and gents, that's it for today's lesson. I hope that was informative and you got some good practice with your area. Till next time, bye. See you later.